Hello, it's Brian, and we're going to be doing some hypothesis testing in StatPowers. I'm looking at this problem. It's a very straightforward hypothesis test using the summary stats. We're doing inference on the sample mean, or the population mean, excuse me. And so this is what you call a one-sample t-test. We're asked to test the claim that the mean GPA of night students is smaller than 2.8 at the 0.025 significance level. So they're giving us all the information we need. We have the we want to select the right hypotheses, the null and the alternative. The null is going to always, so we're testing whether the mean GPA is smaller than 2.8. So smaller than 2.8. A couple of the things that we have here. First off, the population parameter we're testing is the population mean. Okay, so we can eliminate the ones with the p. P means proportion, so eliminate those. We're testing whether it is smaller than 2.8. So we want the alternative to have mu less than 2.8, and this is the one that has less than. That's going to be our hypotheses. And it says this test is a left-tailed, right-tailed, or two-tailed. If we are testing whether the parameter is less than some value, that's a left-tailed test. If we were testing greater than, it would be right-tailed, and if we were testing not equal to, that would be a two-tailed test. So this is left-tailed. And now we're given the summary statistics, so we can use this to calculate the test statistic and the critical value and to see whether we reject or not. So this is using the classical approach. We're going to, so I'm going to go into StatPowers and under analysis, one sample, quantitative one sample. This is where this is found. All the way down, t-test for the mean. I open this up and I'm going to click on enter summary stats because that's what we've got. Okay, and so we are told, sometimes when it loads up, the sizes of these input windows, they're a little too small. I just refresh it. Okay, I have to figure that out. That's okay, so t-test for mean. Let's go down here. Enter summary stats. So we want to put in all the information that we have, including, first off, that the significance level is 0.025. We were told that. Now we're told the sample mean is 2.77 and a standard deviation of 0.07. And we'd have a sample of 35 people, and we want to put in our hypothesis. The null hypothesis is that the mean is equal to 2.8. The alternative is that mu is less than 2.8. Once we put those in, then we get everything that we need to answer this. It asks us to round it to 2 decimal places, so I'm actually going to go up to the top of the screen to the settings and change the precision to 2, just so that I'm sure that the rounding is done. I could round it myself, but why do it myself when I can use this? So it says that the test statistic is negative 2.54, and that the rejection region, the critical value is negative 2.03. In fact, if you click here, you get a little picture that shows you the critical value in my test statistic, and you can see that my test statistic is less than the critical value. It's in what we call the rejection region. So, but I'll put in the critical value. It's negative 2.03. Based on this, do we fail to reject or reject? If the test statistic is in the rejection region, then we reject. And then I'm going to just check my answers. Everything is correct. Okay, now this is another problem that's very similar, but this time we're asked for the p-value. Of course, there's not going to be anything different that I really do in StatPowers. I just use the p-value instead of the rejection region. So it says that I'm going to just put this stuff in one by one. I'm going to actually make this a little smaller so that it will fit a little like right next to the screen. Okay, so I'm told that I'm testing whether the mean GPA is larger than 3.5. So I'm testing mu equals 3.5 compared to mu greater than 3.5. Or okay, this is the right one. The null hypothesis always has to have equality in it, It doesn't have to always be equal. It could be less than or equal. The math is the exact same. Really, so the null and the alternative could be completely complementary, or the null could be just equals and the alternative could be just greater than or less than. That's okay. It doesn't really change things. At any rate, the test, this is a right-tailed test. And now I'm given the sample statistics. Based on the sample of 60 people, the sample mean was 3.55 and the standard deviation of 0.04. Okay, so I'll put all this stuff in. First, the significance level is 0.10. The sample mean, oops, oh, my my little image just disappeared. So I have the sample mean was 3.55, the standard deviation 0.04, and there was a sample of 60 people. I'm going to put in my hypothesis test info, 3.5, and I'm testing greater than, and 2 decimal places. Okay, so my test statistic is gigantic, 9.68. 9.68 is a huge test statistic. Anything greater than 3 or less than 3, and this is the negative 3, is alarmingly extreme. So the p-value is basically 0. It rounds to 0. Although it's technically not 0, it's 0.0000 something. It rounds to 0, to 2 decimal places. This is a clear and emphatic rejection. We reject the null hypothesis. This is very strong evidence at the 0.10 significance level that the mean GPA is greater than 3.5 in this population. Let's just double check and see everything. Everything looks good. So here we have one where we have some data. It says statistics students believe the mean score on the first statistics test is 65. The instructor thinks that the mean score is higher. She samples 10 statistics students and obtains these scores. So we're going to do a hypothesis test, and we're going to calculate some of this stuff. In fact, I think some of this is, we might have to use a calculator for it. Let's copy the data first off. Okay. And I'm going to go for the t-test for the mean. I'm going to use data. Now, the students think it's 65 and the teacher thinks it's greater than 65. So this is what the alternative is going to look like, mu greater than 65. So I'm going to go and click that. Okay, the mean of the sample, well actually let's go back to our summary statistics to get that. I have to click calculate now to get this updated. 69.44. The standard error, now that's actually not going to pop in. I feel like that should probably be done automatically. The standard deviation divided by the square root of the sample size, which is something I'm going to have to do on my own. Let's pull up a calculator and do that. Let's do, so we have 9.22 divided by this, put in 10, this calculator, I have to put 10 to the power of, there's not a square root button on this for some reason, 10 to the power of 0.5, that's a square root. So 9.22 divided by that, so 2.9156. I'll just copy that. That's my standard error. I don't really need that to, I get the t statistic from here. The test statistic is this 1.52, and the p-value 0.08. And at a 5%, 0.05 significance level, I am not going to be rejecting the null hypothesis from this. If we look at the picture, we have the test statistic in here. This is within the realm of plausibility based on the null hypothesis. This would be like kind of the extreme tail. We're not in the extreme tail with our test statistics, so the data that we've collected does not refute the null hypothesis. So we're going to fail to reject the null hypothesis. And it says hopefully you drew a picture. Well, this is a picture basically of the distribution of the sampling, the sample of the test statistic distribution. Here's one where we're doing matched paired data. a paired t-test, it's called. Now, it says you wish to test the following claim at a significance level of 0.005, which is a very, very strict, very cautious significance level to use, where you want to be very sure that you're not rejecting the null hypothesis when it is actually true. You want to be protecting yourself from making a type 1 error. For the context of this problem, the mu d equals mu2 minus mu1. All right, that's good to know. Where the first data set represents pretest and the second represents a post-test. All right, and so we're given the null and the alternative. We believe the proportion difference, the population of different scores is normally distributed, but you do not know the standard deviation. You obtain pretest and post-test samples for 231 subjects. The average difference is d bar equals 0.6 with a standard deviation of the differences of 5.6. So this actually, when you're doing a inference on these differences, even though you have before and after, so we're taking the after minus the before, and that gives us the difference. That's the change. We're really just going to be doing one sample inference on the change. And so I'm going to just do a one sample t-test just like I did before, where I enter the summary stats. So I'm going to go down in here, put in the significance level, 0.005. The sample mean, even though it says x bar here, I'm going to put in the d bar, which is 0.6. The standard deviation it gives was 5.6. And the sample size, 231 students. And so the null hypothesis is that the mean is equal to 0, and the alternative is that it's greater than 0. In other words, we're testing whether the average change was a positive change. Going through here, I get the test statistic rounding to 3 decimal places. I'm going to just copy the first 3 decimal places, copy that over. The p-value is here, rounded to 4 decimal places. It's already set at 4, so I'm going to copy that over. And the p-value is, it's greater than alpha, right? Because alpha was 0.005, and so we would not reject the null hypothesis. We want to fail to reject the null. Remember, always, you'll be asked if you accept the null. You never accept the null as a decision because the null is assumed to be true unless proven otherwise. We're never proving the null hypothesis true. The null hypothesis cannot be proved true. The null hypothesis is assumed to be true unless we find an alternative that is supported by the evidence. So that's the nature of this thing. It's not like we have no prior assumption and we have 2 hypotheses and we prove one true or we prove the other one true. That's not the paradigm that we're using. What we're doing is we're saying, okay, we come into this assuming the null hypothesis is true. We look at the data and we say, does the data refute the null hypothesis? No. Well, then we continue to assume the null hypothesis is true. We don't fail it. We don't change our conclusion about, we don't change our opinion about the null hypothesis. We just don't take action. So the way we would interpret this, we would say that there's not sufficient evidence. So we'd say there's not sufficient evidence to warrant rejection of the claim that the mean difference of post-test from pre-test is greater than 0. To refute the claim, no, that it's equal to. It is not sufficient evidence to warrant rejection of the claim. No. It's the fourth one. There is not sufficient evidence to support the claim that the mean difference of post-test from pre-test scores is greater than 0, right? The evidence, we really are looking at, does the evidence support the alternative hypothesis? And that's the way we look at a hypothesis test. Let's see. Everything looks great. Okay. Now let's go to a matched, like a paired data problem where we have the data and we want to calculate the stuff. Ooh. Here's one. Here's a little one. We have just a tiny bit of data. All right. So here we want to do the same thing except we have the data. We want to test the null hypothesis at a significance level 0.005. For the context of this problem, μd equals μ2 minus μ1, where the first data set represents pretest and the second represents a post-test. So we're going to have to be a little bit careful with this one, but let's see what we do. So this is quantitative. We want to do 2 dependent paired samples. Okay, so I'm going to put the data in. Now I'm going to, because StatPowers at the moment calculates for paired, it calculates the first column minus the second column always. We need to put in the post-test data in this column and the pre-test in the second column. So let's put in the data, negative 8.8, and then I'm going to do 41.8, 64.8, tab 69.3, 74.7, tab 56.7, and then 73.6, tab 81.2. I'm going to add in an option so that you can select whether you want to do column A minus column B or column B minus column A. So at any rate, I'm going to now go down to the t-test for the test for the mean difference, and I'm going to click calculate to get this updated. But every time I update stuff, I'm going to put in the significance level 0.005, just like we had a second ago. The test is that the mean is equal to 0 compared to the mean being less than 0. And now I get my test statistic, my critical value. So my critical value is this rejection region, which is this to 3 decimal places would be negative 5.841. The test statistic is negative 0.78, 3 decimal places. I think that's rounded already to 3 decimal places. And then the p-value, well, we're not using the p-value approach here, we're using the critical value. That's fine. But the main thing is the t statistic is not more extreme than the critical value. It's not in the rejection region. It's not less than negative 5.841. So it is not in the critical region, and it leads to the rejection. We fail to reject the null. As such, there is not sufficient evidence to warrant to support the claim that the mean difference of post-test from pre-test is less than 0. That's the conclusion that we're going to make. Let's just double check our answers. Everything is correct. All right, so this is how you can go about using StatPowers to do these one sample and paired sample t-tests. And I didn't actually go into confidence intervals, but the confidence interval estimation is done really just a matter of setting. You just set the confidence level, and then this is going to calculate the mean difference for you. It's really very, very straightforward. So anyway, that's that. Bye.